Exam 2 is coming up. You guys will be having it soon, this Thursday, during normal class time. Think of the same as Exam 1. I will admit, the Exam 2 that we had to have last semester, this was the easiest exam for the semester. I believe the average was an 85. So, if you're thinking this is going to be in another Exam 1, don't worry. You can rest easy, heroes. Another thing is, Professor Ding has decided to remove a couple of topics from this Exam 2 that we had to deal with personally. Those topics just so happened to be the hardest ones on that Exam 2. So you guys should be in for a perfectly fine exam. It should not go bad. As long as you have studied, you will be fine. Alright? I guess the bad news, this is not going to apply to Exam 2. This will apply to the final or Exam 3. Is those topics that were removed are now going to be on Exam 3. And those topics require that you remember BFS and DFS. So make sure you don't forget those after you've taken this one, because they will be coming back, and they will be harder versions of them. Alright? But as for Exam 2, you guys will be fine. I'm sure it will not be that bad at all. Like I said, most of it was pretty easy. I think the time complexity part on that last question might be the most difficult part. So I'll make sure to go over that. But otherwise, that's about it on the overview for Exam 2. Did you guys have any questions before we went into the actual meat and potatoes of this thing? Yeah, that sounds about right. Okay, we can get started then. Okay, so let's go on ahead and take a look at this cheat sheet here. Cheat sheet seems self-explanatory. It gives you all of the pseudocode for all of your functions, which is good. The most important ones, I'd say, are Kruskals and Prims, in case if you've forgotten them, or if you don't remember how to do... Oh, is it being recorded? Yes, it is. In case if you don't remember how to do them, they're always there so that you can look back on them. But if you have the high-level idea of Kruskals and Prims, you probably will be fine. Those are just there to remind you in case you forget. Same with BFS and DFS. If you've forgotten high level, you can read through that and it will remind you. The pseudocode is not as integral to succeeding as it was in the first exam. It's just there as a helper now. It's not as important this time around, so you should be fine. From my experience, the only time I really needed it was for the heaps. And that was just because when you delete a node, it doesn't become null. It's different. You'll see that when I get to question 1. So I personally messed that up on the exam, so that's why I remember that. Other than that, I don't think I really needed the pseudocode. So the rest of it should be fine. One final thing to mention: union calls Findset for both x and y. So remember that. Pseudocode, or it's on there, so you know, because you know what Findset does. It causes compression. Other than that, though, that's about it for the cheat sheet. It's honestly not that necessary this time around. As long as you know how to do the problems, you'll be fine. So, unless if anyone has any questions. Okay. Looks good enough to me. Then we can go on and get started. So let me move on here. Could it ask for union without path compression? Oh, I mean, yeah, that's perfectly possible. It's just it'd be a much easier problem if you had it without compression, because then it's just a matter of you change 2 things, I think, for union without path compression. So if that were to happen, you'd be lucky. Do you think we'll be asked a number of calls on anything? Not that I know of. I don't think that relates at all to this. If you're talking about number of heapify calls or number of decrease key calls, no, I never had seen that on my exam, and I never saw that on my mock exam either, so I doubt it'll be on there. Okay, so let's go on ahead and get started. So here we go. This is the mock exam. We have 6 questions on it. It's going to go through heaps, then disjoint sets, then undirected graphs via BFS, DFS, MSTs of Kruskal and Prim, and then finally the time complexity. You'll see your answer sheet here. Question 1, it's not asking 1 through 5. It'll ask for whatever it tells you, so don't assume it's 1 through 5. Make sure you read that carefully. Question 2, same thing. It's not even asking 1, 2, 3, 4, 6. It's asking 1, 2, 4, 6, 9. Read that carefully. Don't put in the wrong number, because you can screw that up otherwise, and then you'll miss the points. Question 3, you're going to answer in D and pi. So D is the distance, because this is a BST. D is distance, and stands for distance. Pi stands for root. I'll explain what those mean later, but for now, just know the words. D is distance, pi is root. For number 4, D is not distance because we're going to be doing a DFS there. D is discovery time. F is finishing time. Pi is still the root. Pi will be consistent. So, but yeah, D is not discovery here. D is not distance here, it is discovery, okay? Then F is finish. Number 5, that's self-explanatory. Just find in what order you got the edges, we'll get there. And then number 6 is just like, hey, what complexity is it? Put that in there. So, that's about it for the answer sheet, so you know how that's formatted. Beyond that, we can get started on the whole thing here. So before I get started on the main exam, are there any general questions anyone has about the exam or anything like that? Okay, cool. I'm gonna get started then. Let's go on ahead and pull this up. Here we are. So here's question 1. We've got a min heap with capacity 20 and size 6 as shown here. Awesome. So we've got this. First thing, before I even read A, B, and C, I'm going to construct the heap. So we have 11, and then 17, 13, and then 19, 23, and then 29. All right, so that's my given heap. We're good so far, I presume, on that. So, great. Now, let's start with A. Show the result after applying heap extract min to this min heap. Okay, sure. So we have to apply heap extract min. So the high level idea, of course, is, let me go on and copy and paste this heap here down to A. The high level idea is, of course, you get rid of the 11, you put the 29 up there, and then you just heapify it until it looks like a heap, right? That's the very high-level idea. So we'll go through that motion first, but I do want to do it in a specific way so we can get the correct full answer, and I'll show you what I mean by this. So what I'm going to do is this, right? It's a heap extract min, so theoretically 11 gets stored outside somewhere because that's what was supposed to happen. And then 29 and 11, once that happens, then you have 29 here, right? 29 is going to replace the 11 there. Once that happens, the heap size is going to be subtracted by 1. So it was originally 6, right? But now it's only going to be 5, meaning this number on the right of that line is out of the heap now. Okay? Once that is done, then we have to do max heapify, so I'm going to do that. So we're going to have 29, all right? I'm going to compare it with the left, that's 17, okay? But I'm going to compare it with 13. 13 is smaller, so I'm just going to do this like that. 19, 23, and then remember 29 down here is out of the heap. 29, I mean, it can't go any lower because it doesn't have any children to connect to. Because of that, that is the heap for A. So, good, we have that. And now what we need to do is we need to write down the array for said heap, right? So we have the heap, but we have to write the array for it. So 13 is in spot 1, right? Because it's at the top. Then 17, then 29, then 19, then 23, then here's the thing, right? Even though this is out of the heap, it is still in the array, technically speaking. It was never deleted. Because of that, you have to write 29 here again, because it was still there the entire time. We never got rid of it in any way. So once that's done, then the answer sheet asked for 1, 2, 3, 4, and 6. So you will be reporting those answers accordingly. Let me check to see if that was the answer for 1A. 13, 17, 29, 19, 29. That was right. Yep, that's the answer. So there you go. A is done. Any questions on that one? The main confusing thing is this, but other than that, it didn't seem to be too bad. Were there any questions on that? Or are they depth first? What do you mean by that? We're not searching here, so we're not doing anything related to BFS or DFS. This is just heaps only. Uh-huh. We removed 11, pulled the 13 upwards. So, okay, no, what I did was, so there was originally an 11 here, right? What I did was, because 29 is the last element, what I do is, okay, 11, I'm going to save it and store it outside this function, and then I will forget about it, right? I took the last element, 29, and I replaced the top with it. And then once I did that, I subtracted the heap size by 1, which takes 29 out of the heap. So when I'm doing any heap equations or any heap functions, I'm not going to even consider that 29. It's as if it doesn't exist. In reality, it is still in the array. So what ends up happening is then I do the whole heapify thing, and then it turns out, 29 is still there at the end. That's what ends up happening. If you're wondering why it works specifically this way, it's because this is where the cheat sheet comes in. This is what I was talking about when I said I missed it on my exam. If I see right, you can see max heap extract max. You can notice that, you set your max. You can notice that A1 is equal to A of heap size. So the head element is equal to the last element, which is what we did here, right? I set 11 to equal to 29 after I got 11 via getting the max heap maximum. And then once I did that, I just max heapified everything and I returned the max, right? The idea is, you get the 11, then you override it with a 29, then you max heapify the 29 until the heap is good. Once you've done that, then you subtract the heap size by 1. This 29 never gets deleted from the actual array, even if it's removed from the heap, so you have to report it. Hence why there is a 29 at the end. So does that make sense? Okay, cool. I think that's it. That was the hardest one for this one. The rest of them are pretty self-explanatory, so let's just go through those real quick. Okay, so B, it says heap decrease key A, 6, 0 to the min heap. If you're having trouble with reading what this means, the A, 6, 0, the pseudocode will show you that. So we have, this is not a decrease key function, but it's the increase key. It's kind of the same formatting, right? It says A, I, key right there. So now we know that the second number is the index, the third number is the actual value. So now we know that it's looking at index 6 and it wants to put in the number 0. So that's what we'll do. So we're going to check index 6 right here and we're going to decrease the key to 0. Good enough. Once that happens, since we call decrease key, we're going to move up. And every time the parent is larger than the 0, we're going to keep moving up, since this is a min heap, right? So there we go. Now the idea is, I'm going to write this, 19, 23, those don't change. The 13 is smaller because it was the parent of the 0, so we move it up. And then the 11 was smaller, so then we're going to just move that up. Like that. Once that's done, then again, you take this heap and you represent it as an array. So 0, 17, 11, 19, 23, 13, and 1, 2, 3, 4, 6. Okay? And that would be your answer, which I believe is correct. Oh, that's not the wrong thing. Yeah, 0, 17, 11, 19, 13. Perfect. Yep, that's right. Any questions on that while I set up this next one? Okay. Alright, then I'm going to go on and move on to C. That one wasn't too bad. Here we have min heap insert. So again, we have this. And the idea is we're going to insert an element into the array. Remember, when we call insert, it always inserts at the end. So just put in a -1 there. Once you've done that, you're going to follow the decrease key method for ensuring that this is a heap where you just move the number up. So -1 is indeed less than 13, so we're going to do that. And then the 13 is going to switch here, and then the -1 moves up again. This ends up being your answer, right? And now represent it as an array. Just write the thing out. 23, 29, 13, 1, 2, 3, 4, 6. And that would be your answer, which I believe -1, 17, 11, 19, 29. Yep, that's right. There you go. The answer key is missing 23 in all of these, right? Yes, it is. 23 is the 5th element. In your answer sheet, it asks for 1, 2, 3, 4, and 6. It is ignoring the 5th entirely. So yeah. So there we go. And we got all of that going for us. Good. Some sound. I think someone just didn't have their mic muted. Whoever it was, they're probably fine now. But anyways, yeah, so that would be your answer for C, B, and A. So that's number 1. So the heaps should not be that bad. It could either be a max or a min heap, so keep that in mind. It doesn't have to be one or the other, but the process to complete them is just the same. All right. Any questions on that? This one is not that bad. So, no, or max, like a max heap or a min heap. So that's about it. So, that should be it for question 1. I don't think there's much on this. I think most people got this. Okay, I'm going to move on to question 2. If you do have a question, mention you have one and then say it so that I know. But otherwise, yeah. So we can move on to question 2 then. So here we go. We got disjoint sets, right? Assume we're using path compression with everything. All right, that's fine. So we are given a disjoint set structure with this array. Okay, and then we have some sub-questions to answer with this. So before I even look at said sub-questions, first off, I'm going to convert that array to a tree, right? Now, I know you guys are... Professor Ding did show how to do trees one way. I believe it's like where everything is centered like this. I don't know, like this, and you put arrows or something like that. When I did mine, I did them a different way. I kind of turned them into like trees, and I'll show you what I mean. So, here, first off, I'm gonna look at the number. I'm gonna look at the indexes that have negative numbers, which is 1 and 6. They both have -3. So what I'm gonna do is, okay, I'm going to write -3, and then pointing to it is 1. Okay, for 6, -3 pointing to it is 6. Now I'm gonna focus on one set at a time, right? So I'll focus on the -3 with the 1 pointing to it. Here, the next I see is the 2 has a 1 in it. That indicates that the 2 is pointing to 1. So I'm going to write that. The 3 has a 2 in it, so that means 3 is pointing to 2. The 4 has a 3 pointing in it, so that means that the 4 is pointing to a 3. The 5 has a 3 pointing at it, so that indicates 5 is pointing to the 3. And that's good. Next, we have the 6, so okay, that's fine. The 7 is pointing to 6. 8 is pointing to 7. 9 is pointing to 7. 10 is pointing to 8. Like so. Why did I start with -3? Oh, because the -3 indicates the actual height of the tree, right? So what I do is I record that with whichever set I have there. So I know for every set or every tree, you could say, I know what height they're at. That's important for union because your union, you have to make sure that you have, you have to make sure that you see the heights correctly there. Okay, that's why I start with -3 to indicate, hey, this is a pointer that is pointing to a negative number, which means it would be considered, I guess, a home pointer, which I'll talk about in a second. Anyways, so this is how I do it. I know, how is the height 3, by the way? It was given. That's it. It was literally just given. That's all. So, with all that said, yeah, this is how I do it. I know some people have done it right in that kind of like row and column matrix looking type of way. I haven't learned that, so I wouldn't be able to show you how to do that. But I'm pretty sure it's just like how you draw it out. You're ultimately doing the same thing. So I think you will be fine here. Anyways, with all that said, now we can actually start looking at A, B, C, D, and E. So for A, show the result after applying Findset 4 and Findset 9 to the disjoint set at the start of this equation. So keep in mind, these are our raw sets. So I'll just go on and say that there. So those will be what we start off with. So I'm going to start with A. A says Findset 4 and 9. So let me go on and just take these and copy these. Actually, no. I'm going to start with this one only. Copy and paste. Like that. Good. And the idea is this, right? We wanted what it said, Findset 4. Meaning, we have to first be able to get to 4, right, via our pointers. So we're going to go backwards on these arrows and get to there. So now, -3 is not a pointer, so I can ignore that one. I'm going to start with 1, okay? Now, the pointer I start with, I like to call it the home pointer. That is the very first pointer that you will focus on, right? And the reason why I distinguish this one from the others is because every pointer after the home pointer, if I touch it, it must point to the home pointer after compression. So I just touched 1, so it's the home pointer, so I won't move it at all. But now I have to go down and I'm going to touch 2. So now, after I fully compress this, 2 needs to be pointing to 1. Luckily, 2 is already pointing to 1, so I don't have to do anything. Then I'm going to go to 3. Now, 3 is currently pointing to 2, but I'm going to have to make it point to 1 after everything is said and done. So, with all that said, then I can finally hit 4 here. And now that I have found 4, I can stop. And I have to now recreate my tree with compression. So, that's what I'm going to do. So we have -3. 1 is still pointing at it. Or, oops, no, not like that. 1 is still pointing at it because it was the home pointer, right? 2 is still going to be pointing at it. I'm going to write it off to the side here. But now 3 must be pointing to 1. And 4 must be pointing to 1. Now we notice we never touched 5 at all. Meaning whatever 5 was pointing to originally, it'll keep pointing to that. So I'm going to write 5 pointing to 3. This is my compressed node, or my compressed tree after completing Findset 4. Right. So there we go. That is my first tree done. Now I need to do this tree up here. Before I move on to that, were any questions so far, or do we all got this? Is this going good? Okay, it looks like we're doing fine. Could you do it one more time? Okay. I mean, I'm gonna do it. I'm gonna do it one more time with this. So watch this one. All right. So here we go. Again, I have this whole like raw tree that I made, which is fine. I'm going to find Findset 9. So 9 is there. I have to start at the first pointer I meet. So 6 is going to be my very first pointer, right? This is my home pointer. Home, right? Meaning every other pointer I encounter after the fact will end up pointing to 6. Now, next is 7. 7's pointing to 6 already. That's good. Then there's 9. Okay, 9 will have to point to 6 once I compress it. Well, I just hit 9, so I am done. I'm not looking for any more pointers. So I'm going to rewrite -3 and 6. That's fine. But now, 7 is going to point to 6, and 9 is going to point to 6. Okay? We see 8 here. 8 was already pointing to 7, and it didn't get touched at all, so it'll stay pointing to 7, and 10 will stay pointing to 8. This is going to be my compressed tree here. Does that make any sense? Okay, good. I can erase that then. Alright, so once we have fully compressed our tree, we now have to write it in an array version. So to do that is this. First, I'm going to focus on this tree here. I'm going to write that array version. So index 1 is pointing to -3, so I'm going to write that. Index 2 is pointing to 1. Index 3 is pointing to 1. Index 4 is pointing to 1. 5 is pointing to 3. And that's it for that tree. Okay, good. Next, I'm going to do this tree. 6 is pointing to -3. 7 is pointing to 6. 8 is pointing to 7. 9 is pointing to 6. 10 is pointing to 8, I believe. And there we go. Once we have that, I'm going to look at my answer sheet. I'm going to check the specific numbers it wants. 1, 2, 4, 6, and 9. Okay, 1, 2, 4, 6, and 9. So the answer is going to be -3, 1, 1, -3, 6. That will be my answer for question 1, which was right. Any questions on that? That is how you do Findset. What's up?
Would you be able to scroll up just a little bit so I could screenshot it?
Oh, I got you here. I'm
Thank
going to
you
be
so much.
uploading the files, by the way, so...
Oh, perfect. Thank you.
Yep. Are we good on that? I'm pretty sure we are. Okay, good. Alright, I'm gonna move on then. Okay, B is much simpler. The main reason is we already found our find sets for 4 and 9, so B should be a lot easier since we can just use these. So I'm gonna go on and put our find set trees here that we already found in A, so I don't have to do any extra work. Let's go on and put that. So these are compressed. I'll just write that down. Those are compressed. Okay, good. So what is B asking? Show the result after applying union 4, 9 to the disjoint set at the start of this question. Alright, sure. So let me go on and select these again. I'm just going to copy them, paste them down here. So the idea is we're going to write union. And to do union, right, we have to first compare the heights of... We have to first find out what find set 4 belongs to and what find set 9 belongs to. So this is 4, this is 9. And so to get find set 4, we just have to go all the way to the home pointer, which is 1. And then for 9, we have to go to the home pointer, which is 6. So really, this is going to be left tree versus right tree, right? So we have to union both of those. Good. Okay, easy enough. So now that we got that out of the way, next question, what do we do with union, right? First, we have to compare the heights of both trees, which in this case is, this has a magnitude of 3, this has a magnitude of 3. If they are the same, you will take the second tree that was mentioned. We said union 4, 9. Because of that, the 9th one was the second one. It takes precedence. So what we do is we add 1 to the magnitude of this tree's height, right? Or you could just say subtract 1 from the second tree. Once that happens, this tree will now lose its height. And instead of the 1 pointing to that height, the 1 will now start pointing to the home node of the second tree. Union 1, 6, no. I mean, that's the same thing. That's the same idea. Like, it asks you union 4, 9, right? but when you do Findset, it'll end up just being the same as union 1 comma 6, right? It's the same thing. But the question itself, I believe, says union 4 comma 9. It's just when you say 4 and 9, 1 and 6 represented, so they mean the same thing. So, anyways, we have this, right? And now, once we've completed this, it's just a matter of writing it in an array format. So I'm going to go in and do that. So 1 is now pointing to 6, so I'm going to start with that. 2, 3, 4 are the same. 5 is the same. 6 is now going to be negative 4. 7, 8, 9, 10 were all the same. So then the answer is 1, 2, 4, 6, 9. Right, that's not 9. 9. So 6, 1, 1, negative 4, 6. There you go. And yeah, that should be the answer. Let me check for B. 6, 1, 1, negative 4, 6. Yeah, that's good. Okay. Any questions on that one? Okay, good. C is the exact same thing, but you're just switching the two, so then you just have to switch. I'm not even going to bother doing it because it's just the same thing. D is, this time around, you have to... the only reason I wanted to do this one is because it says show union of 5 comma 10. Now, you might be thinking B and C were super easy, so D and E are also going to be super easy. They are, but one thing you have to remember, right? We never found the find sets of 5 and 10. We only found the ones for 4 and 9. Those find sets become useless when you call union of 5 comma 10. Now that I think about it, that's another reason why you don't want to say union 4 comma 9 is the same as union 1 comma 6, because you're ignoring compression. So don't think of it like that. But otherwise, yeah, because 5 comma 10 is 2 different numbers, we have to actually do find set on these two, since we never found it. So that means we have to take the raw sets that we found earlier on, we have to, copy them down, and once we've copied them down, we have to compress them based on 5 and 10, so I'm going to do that. Let me just go on and do that. Here we are, like this. And now I need to do 5 and 10, so I have to go on and compress them. The compression isn't too bad, so I'm just going to do it down here real quick for you. I probably don't have to walk through it. So what ends up happening is 1 is our home pointer, so then because of that, 2, 3, and 5 all have to point towards it, yada yada, and then 4 has to point towards 3, and then for the 10, it's going to be a negative 3, 6 is our home pointer, so whatever. We have 7, 8, 10, and 7 has 9 pointing to it, and all the rest of these point to 6. What happened to the A of 1 equals negative 3 after the union? What was it? For all the way back here in B. So what ends up happening is when you do union, one of the trees, because it's no longer connected to, I believe an actual, a number, because it's not its own set anymore, it's connected to the 6 now, the negative 3 disappears. It's not a thing anymore, because it's connected to another set now. That's why. So you can just drop the negative 3 since 1 will now be pointing to 6. The negative 3 is now irrelevant. The array size is smaller. I wouldn't say that. I mean, I guess you still have all of your main pointers and everything, but no, I don't think so. I wouldn't say that. I'm not sure what you mean by array. It's just A of 1 changes, that's it. What he said, yeah. The array never changes size. All you're doing is you're replacing negative 3 with a pointer to 6. Okay. Anyways, so we did we did compression of find set 5 and 10 here. From there, then you can do union. In this case, it wanted union of 5 and 10. So you just do 5 and 10 union, which just means 10 takes precedence, make that a 4, get rid of that, point that to the 6, and then write the whole shebang, alright? I think we all got the point of this. We don't need to beat this any longer. Alright, any questions on this, or are we good? Can we call it? What's the time complexity of this thing? We will get to that. That's a question 6 question thing you're asking. So we will get to that. Okay. Are we good? All right. Okay. Let's move on to BFS. Okay, good. BFS. They really gave an easy graph for this one. So, okay, we have an undirected graph up there. Do BFS on it. Start from A. Okay, I'm gonna just rewrite it down here, which is just like that. Okay, good. And now do BFS on it. So the way I do it is just rewrite the nodes in a list like this, and then make 2 categories here. The second one will be pi. Pi is always at the end. First one is D. It's BFS. So we're focusing on the distance, right? No times here, just distance. So we start with A. Good enough. Okay. Since we're starting with A, that means that our root is going to be guaranteed nil and our distance is guaranteed 0. Your start node will always be like that. Okay. Remember, this is in alphabetical order, so whichever ones you interact with, the first one has to be in like the earliest alphabetically. Beyond that, you can get started. So A's distance is 0. That's pretty obvious. We'll hit C first. That distance is 1. It came from A. Then we'll hit D. That distance is 1. It came from A. So once we've done that, I'm going to jump now into C. C is going to be what I'm looking at. C is not connected to anything, so anything that's not been discovered, so I don't care. Now I have to jump to D. D is going to... Actually, wait, did I miss a... Actually, no, did I miss... Oh, I missed a line. Oops. Okay, never mind. Okay, C is connected to B, so then you have to do 2 and then C. There you go. Okay, my bad. And that's all of them, all the distances found. That was about it. This question was kind of really, this graph is really easy. Also, it's an undirected graph, so it's going to be very easy to easily find everything. I'm not sure why we didn't get a directed problem, but, you know. And directed is just the same thing, but it takes longer. You probably won't need it. You can just apply this. So, I mean, any questions on this? The idea is we found the distance and the predecessor. This is the distance, this is the predecessor. So, there you go. I mean, that's about it. I don't think there are any questions on this, right? Do you think any questions will give us adjacency matrix instead of the picture? No. No, you are guaranteed the picture. Okay, I guess that's about it. Alrighty then. Time to move on to question 4. Here we are. It's literally the same thing, but just do DFS instead. So, again, write A, B, C, and D. Now this time, I'm going to write D for discovery time, F for finish time, and pi for root. Right, so pi means the same thing. D is discovery time. Right, F is finish time. Actually, before I get to this, sorry. Do you guys know what this D value means? This is distance. Do you know what that means? Is that fine with everyone? I saw no questions, so I assumed that was fine. Does everyone know what that means? I know you guys... Yeah, distance from A, yes. Distance from the root. Okay, yeah. You guys did an assignment on it, if I remember right, so I shouldn't even be asking this question. You should probably know this. Yeah, okay then. Yeah, just distance from the root. Good. Okay, you guys got it. Then you'll probably know how to do this as well. So, let's just quickly go through it. We're starting on A. Alphabetical order as always. So, because we're starting on A, we can say that that is nil. And now we have to do D and F. So, because we're starting on A is the first one we discovered. That's discovery time 1. Okay. And now we have to check its connections. It has C, so I'm going to go to C. C. We came from A. This is discovery time 2. Okay, C is connected to B and D. B goes first. I'm going to connect to B. Discovery time 3. And then I'm going to connect to D. That is discovery time 4 from B. Start at 1 instead of 0 this time. I mean, I always started from 1 when I did my... Oh, yeah, yes. For DFS, you always start from 1. BFS, you always start from 0. Distance is from 0. Time is from 1. Okay? So, anyways, so we just finished discovering D, which was the last node to discover. Because of that, we have to finish up D. So I'm going to do that, and I'm going to fill it in. Okay, then I have to go back through this route back to B. Alright, that's 6. I'm going to finish up B. Go through the route back to C. That's going to be 7. And finally, there's A. And there we go. We got the whole DFS done. That's it. Could we do a directed graph example on DFS? Yes, I am willing to do extra examples for these questions because some of them have been kind of really easy. But I want to do those after I've gone through the entire exam because I know that people do want to hit the time complexities. So I want to get that first, and then we'll do extra examples, alright? I'll make up some problems then. Alright, I'm just shooting through these so everyone's got the basics down. I can get that down pat before we get to question 6. I'm going to have A, D, B, C, but like, I'll just point some arrows to places, like that. I don't know. Actually, no, I don't want to do that. I want to do this one. There we go. We have the arrows pointed, okay? So, using that graph, I want you to do BFS on this. So, we're going to do A, B, C, D, and since it's BFS, I'm going to get distance and root. That works. So, it started node A, okay? So that because that A is nil and its distance is 0. So now what we have to do is we have to travel through and try and see how far everything is alphabetical order. So I see C, so I'm gonna do C first. That's 1 coming from A. I see D, I'm gonna do D next. That's 1 coming from A. Okay. An arrow is connecting from A to B, but it's pointed the other direction, so I cannot use it. So that sucks. Oh well, nothing else I can do about that. Actually, I'm gonna erase this arrow for the sake of this. That's actually not even going to work, is it? Oh, okay, never mind. Let me change this graph a bit, and then I'll reset the problem. Let's do this instead, just to get a different answer. Okay. So again, A is nil. Okay, I see C. I'm gonna do 1 and then A. I see B, but like the arrow is pointing the wrong way, so I can't do anything about it. And then I just have no connection to D, so I have to move to C now. I see D, 2 coming from C, but I don't see anything else. Okay, so that's about it for C. And then I see D. D is pointing towards B, so I can do that. And then that's it. I have discovered B. I've discovered all 4. That's it for BFS. So the only difference between undirected and directed is just the arrows actually point. So now you can only go one way. Other than that, it's the exact same thing. There's no other difference. DST will be the same way, which I think I have an idea for that one, but yeah. Okay, so I'm gonna do DS. Oh, whoa, calm down there. No, open that back up. Okay, good. So that's about it for that one. I'm gonna move on to number 4. We're gonna go back. Okay, we're gonna use that again. So A, D, C, B. We're gonna start at A, point to C, point to B, point to A, point to C, and I don't know, point back to A. That works. Okay, sure. So I'm gonna do A. Could you have them weighted? Weights don't matter. When it comes to searching, it doesn't matter. Only algorithms will be affected by weights. But when you're doing BST or DST, weights do not matter. They're insignificant. D, F, pi. Okay, good. So we're going to do A first. So that's just, nil, because we just started at A. And we're going to have discovery time 1. Good. C is going to be discovery time 2. Awesome. Because that was the only thing that A is pointing towards. The only thing C is pointing towards is B, so discovery time of B is 3. I can't connect to anything else, so then that's... Oh, wait, right, I should probably write this. Oops. Wait, A and then B. Okay. B can connect to A, but A's already discovered, so I can't do anything about that. B can't connect to C, but C's already discovered, so I can't do anything about that. So then B's done. That's 4. Get rid of that. Whoa. That's not what I wanted. Okay. Then C can't connect to anything. That's 5. Get rid of that. Stop. Okay, and then A is 6, so then put 6. Get rid of that. And that's it. Now you might notice I never touched D once, because D has 0 connections with anything. It's because of that if you ever encounter something like this, after going through every other node, you must just assume that you can immediately start going on a new node next using alphabetical order. So if I had like D and E and neither of them had any connections to anything else, I would start with D in that case. So now I'm just going to do D, which is 7, and then it's nil because I couldn't really start from anywhere. There's nothing to connect it to, so then it's done, and that's 8. Oops, there we go. And that would be how you would do a graph like this with a directed version on it. That would be it. B's predecessor... Oh, oops, I wrote that wrong. Yeah, let's see. Okay. Good, that should be it for that. Is that all? Okay, should be good. Alright. This was so much easier than the first exam. God, this is so much easier than the first one. Okay, here we go. Kruskals and Prims. Yeah, you guys don't even have to do the stupid SCC stuff. That's for later. That's good. I'm gonna have a hell of a time explaining RBT on exam 3. That's gonna be rough. Ugh. Let's go on and finish up this one. Okay, so... Okay. A. Use Kruskals. B. Use Prims. Alright, good enough. Let's start with Kruskals. Kruskals is... Alright, let me explain the high level of Kruskals. So the idea of Kruskals is... both of these algorithms are greedy, right? Greedy means... I appreciate the compliment. Greedy means that you are going to try and take the easiest path always, right? So when we're looking at these two algorithms, we're talking about, like, you know, different ways of being greedy. In this case, Kruskals is saying, okay, assume you're given literally all the edges, all of their weights, all the crap like that. Like, we are given all of those, right? What you're going to do is from least to greatest, you are going to list all these edges. So I'm going to list BC, then BD. If I see them like kind of equal, I'll just be like, okay, whichever one has the earliest letter. So AD, then CD, then AE, then AB, I believe, yes, and then AC, finally BE, right? So what I just did there is I listed from least to greatest all of the edges within this graph, right? Once I have done that, what I am then going to do is I am going to keep selecting from top to bottom these edges until I get some sort of path that includes every node, and I'll show you what I mean. So I'm going to select BC first. I'm going to really color in that line to indicate I have a network between B and C now. Now I'm going to select BD. I'm going to do that. Now I have a network of B, C, and D. I'm going to select AD. I have a network of A, B, C, and D. I could select CD. I could. But the problem is I already have a network between B, C, and D. And the weight of CD is kind of equal to my network. It wouldn't really matter if I chose this one. So I'm going to get rid of that. I don't need that. Okay. Then finally I'm going to select AE. Like that and there. And because I have all 5 nodes, I'm going to get rid of the rest of these. This ends up being my answer. For the sake of, you know, this, I'm going to go on and keep that in for the sake of notes, but I'm going to write down the actual answer. AE, right? So CD, I cross it out, and then all this crap I never needed to write, so I could just cross all that out. 1, 2, 3, 4, this is going to be your answer. Let me go on and, I'll keep that, and then I'll just, okay, that's good enough, yeah. 1, 2, 3, 4, there we go. And that's how you do it. That's how you do it, Kruskals. There you go. I mean, consider you guys already did the exam, so you're good to go. Edges equals yes, yes. That's the number of vertices minus equals the number of edges. Yeah, but yes. Yeah, there you go. That's about it, man. Nothing more to it. I believe that is the correct. Let me check to make sure, but I'm pretty positive that's good. Where is it? B, C, B, D, A, E, A, E. Yep, that's right. Yeah. All right. Okay, I'm gonna move on to prims then. So we're gonna go on and take prims. B. And I'm gonna put the graph here. And I'll put 2 of them, before and after. Now for prims, it says our starting node is A, our root is A. So I'm gonna go on and circle A down here. Okay, we're starting at that, and the idea is with prims, it's greedy in the sense that every time within your network you see the smallest edge, you take it. That will hopefully get you to the easiest paths possible. So that's what we're gonna do. So we still get a cheat sheet for this exam. I mean, yeah, you get this cheat sheet here, which just has all the pseudocode for every function we had. It's probably not going to be as necessary as exam 1's, but you might need it for maybe I don't know, max heap, extract max, like this one over here. Mainly just because 1A might be a bit tricky, so you can use that to ensure you have 1A right. But otherwise, yeah, the cheat sheet's there, I guess. No bringing your own, same as before. Anyway, so we're going to do prims. So the idea of prims is this. We get a bunch of edges. We want to take the easiest one. So AD seems like the easiest, so I'm taking that one. Oops. Instead of doing this, I'm going to underline them. It looks better. Now I have A and D, and I'm going to write down that edge. Now I have A and D as my first edge, and I have the nodes A and D in my network. So I have to take the second easiest one. I can see that BD is the next one, so I'm going to go on and write that. Now I have AD and B in there. I see BC is the next one. I'm going to have BC in there, and then finally I have to go on and find the next edge. Okay, I see DC here. The problem is I already had D and C in my network, so I'm just going to ignore this one entirely. I see a 4, that's A and E, and I can write that, and hey, I got all my nodes. There you go, yay. And I'm done. That's how you do prims. So the main reason why they want you to do both is because they want to make sure you get the right order, right? You write them in the right path, right? Or the right order, right? So B, C, B, D, A, D, A, E. The actual edges should be the same, right? You should have the same network, but it will literally just be, in different orders, right? You should get the same end network with Kruskals and prims. They should not be different. So if they are different, you can use that as a smell test to figure out, hey, this isn't working. This doesn't smell right. All right? Any questions on MST on either of these? Why can't you get 2 different MSTs? Mainly because assuming you treated them both in the same manner, if there is only one best MST, then the algorithm you're using, unless if your algorithm sucks, it should end up with that MST, and this just so happens to be that best MST. That's about it. That's the main reason. Because, there's no other way to get a better path, right, compared to, anything. If I wanted to, I don't know, use, instead of the 2, if I wanted to use the 3 instead, right? That's not the good MST, because the 2 is smaller and it results in the same, thing. So I want to use the smaller one. The idea of MST is there's only one, right? If you do have multiple, then ultimately it's based on how your algorithm is constructed, but generally there's only one MST that you can find. Could you have different ones in a graph? Okay, well, if I did I get what you're saying. If I did A, B, C, right, with 1, 1, 1, and I started at A, then yeah, I could do A, C, B, and A, B, C. I mean, that's fine, I guess. If I did that, then that's fine. But, or if I did I don't know, I mean, that makes sense, but the idea is try and get the same one if you end up having the equal weights, right? And even then, equal weights doesn't mean there can be multiple, so be wary if Kruskal's and Prims results in a different result, okay? Can you explain questions 1 and 2? I'll do that after. We already went through that, so I'll do it after the fact. So, okay. That was question 5. You know, easy stuff, that's done. Question. What is the worst case complexity to remove an element from the heap while keeping it as a heap after the removal? Right? So, before I go into this, is everyone back? Is everybody here? Then again, my break was like less than a minute, so I don't think it would have mattered, but... Okay, cool. Sounds good. Okay. So, let's do it. Let's see. What's the worst case complexity to remove an element from the heap while keeping it as a heap? Okay, so here's the thing, right? So, when it's asking, we have to look at the actions that it's doing. First off, it's asking we remove an element. Okay, that's fine. And then we keep it as a heap after said removal, right? So we're gonna do some sort of like heap remove function, okay? That's similar to say like, I don't know, heap insert, something like that. Where, you know, with heap insert you're gonna give a and then some sort of key. Heap remove, we could say you're gonna give it an a and then instead of a key, right? Because you know you're not gonna. You don't need a key to remove. You're going to be using an index to remove, is the idea. So if that's happening, then we're going to go on ahead and assume that. So first off, what are we doing? We're going to remove the element. Then we're going to keep it as a heap, right? We need to find the time complexities of each of these actions. Now, first off, if you're just going in a heap, I don't know, like this, sure, something like that. If we're trying to just remove an element, like I don't know, I want to remove like 7, right? Okay, first off, I'm gonna just get rid of it. Dash its hopes away. Like that's time 1, right? That's big O 1. That should not take anything else, right? It's just a single action, so we don't have to worry about that. The problem we have to worry about is we need to keep it as an actual heap itself. So to do that, obviously, once you have removed an element, we have to treat it like the extract min, where we will be replacing it with the 11, right? We replace it with the last element in your heap, and then you're going to do max heapify. Min heapify in this case on that. I guess it just so happens that this is actually perfectly... Wow, they just managed to stay a heap. Alright, I'm gonna replace that. Instead of 11, I'll have like... I don't know, like... There, that works. So like, there. I wanted to delete that number, so now I have to move 256 up here. Right? And now, because of that, I have to, quote, keep it as a heap. And to do this, I have to call heapify on it so that I can actually do that. In this case, 256 is going to be greater than 13. It's also compared to 17, but 13 smaller, so I'm going to then move it down here, right? 256 and 13. Now you may be wondering, okay, alright, I get how the actual element gets removed. I know how to do that. The question is, like, how am I supposed to tell the time complexity, right? Well, to do that, first, we have to essentially kind of help go through the motions of doing the problem so that we can get some insight on it. So what I'm going to do is, I'm going to put that 256 up here. I'm going to put that 13 back. I'm going to try and find the worst case that this could happen, right? The most extreme that could take the longest amount of time. Let's say instead of removing, I'll put this back here. Let's say instead of removing that, right? I'll put the 7 back because I thought I had that. Let's say instead of getting rid of the 7, I want to get rid of the top, the 3, right? It said not necessarily the root has to be removed, but if we're asking worst case scenario, I'm thinking the root would probably take 10 years to remove, right? So I'm going to do that. So I'm going to go on and put this back up here, like that. Now I have to go on and call heap max heapify on it. Well, 7's clearly smaller, so I'm going to go and shift that. 13 is clearly smaller, so I'm going to shift and I have to do that. So what I notice is I had to heapify 2 times, right? I had to go from here to 13 and from here to 256. I had to move it 2 times. Okay, that seems interesting enough. What about, I don't know, let me go on and put this back up here. 7, 13. What if I had like a larger thing, like, I don't know, 19, 21, just like 26, 14, 18, something like that, okay? What if I had a larger one? Now I have to go on and do this 1, 2, 3 times. 256. Notice I added a new level and I had to do it an additional time. Okay, so I see that pattern and I'm thinking, alright, if the number of levels determines the number of times I have to call heapify, well, this clearly is not O of 1. This is something else entirely, right? So, but at the same time, I can't say it's O of n, because, you know, it's not, I don't have to do it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't have to do it that many times. I just do it based on the number of levels, right? So, because it's based on the number of levels rather than the number of elements, or it just being 1, I can then assume, okay, it's probably going to be log n to keep it as a heap. Okay, so it's log n to keep this thing as a heap. And so now that I have that, right, I have to compute the final answer to this whole question, right? I had big O of 1 on one, and in the same scope I had big O of log n, right? Clearly the log n is a larger growth than O1, so I'm going to get rid of that. So the answer would then be log n. That's how long it would take to, say, remove an element and while keeping it as a heap after the fact. Are there any questions on that? I can think of one major one, but are there any questions for anybody else? Is there pseudocode for heap remove? No, there is not. No. The best pseudocode you could use is heap extract max or heap extract min. That is essentially heap remove, except you are forced to remove only the root. But in this case, you could use heap extract max or min to support your claim, or like support your reasoning as to why, you know, doing heap underscore remove is log n. Because heap extract max is an example of that. It's just heapify then? Well, it's not, okay, technically it's not just heapify. It's gonna be, you keep it as a heap, which is heapify, and you're also removing the element. It just so happens that getting rid of the element is big O1, so it doesn't matter. So it is just like heapify's timing, because the removal time is just 1, it's nothing. Would it make more sense to use theta log n? No. No, it doesn't have to be log n. That's the main reason. Actually, well, it actually depends on n, doesn't it? You could say that, maybe. The answer sheet read it as big theta instead of big O. Oh, okay, that's my bad then. Okay, sure. Dang. Let me go on and check to make sure on that. It's probably theta then. I'm probably speaking dumb. Yeah, okay. That would make sense that it's theta. Because, I mean, if it is quite literally the levels that matter, then yes, it would have to be theta of log n. Yeah. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would be 3 times. Yeah, that matches out. Okay, that's 3 times floor function. Yeah. That matches. Okay. Then yeah, it would have to be theta log n in this case. Okay. Does anyone have any questions on this one? Question? Okay. Best case? I mean, if you wanted the best case, I mean, it'd probably just be big O1. Just because, like, I mean, all you could do is just like, oh, hey, it was already here. I never had to move it, so I have to call heapify once, and that's it, you know? That'd be your best case, but literally no human being would ever even consider asking for best case, so you should be fine from that. Are time complexity questions multiple choice?
I don't know. Because I don't think I ever had a question like this. I don't think I ever had this on my test. You guys, I think this replaced your SCC question, so I don't think I ever could say that. But I wouldn't expect it to be. Also, the answer, now that I think about it, the answer sheet literally, like, says it's not. Like, if you look at the answer sheet, it literally is a fill in the blank. So I'm pretty sure it's going to be fill in the blank. So, there you go. Yeah, you always look at the answer sheet to see the formatting of the exam. But yeah. You came up with 2 time complexities, one for removal, one for keeping the heap. Are you always going to choose the larger one for a final answer? Yes, because we wanted the worst case time complexity, and the larger one always takes precedence over the smaller one. This is like test 1. Yeah, I'd already have omega for you. You just put in the function. Yeah. In this case, the main reason why I just took the log n over is because these functionalities happen within the same scope, right? It's because of that I can just override one with the other. If it were to happen where, like, one function was in the other scope, then I'd have to multiply their complexities and figure out the answer, right? So, heap. Why isn't it big O? Because it will... Am I going to post this mock exam? It's up. You can check Canvas. It should be up right now. Well, since you could have constant time... Okay, well, okay, here's the thing, right? Let me say... what? Heapify... Log out. On, like, the explanation... Oh, well, I mean, let's try something, right? Okay, we have this, right? This is technically already heap. Say we deleted, I don't know, something, and then we wanted to do this, and this was the resulting heap, and then you have to heapify, like, this number. I think you're saying, like, you have all these number of elements, right? But you have all those number of elements, right? And then when you're trying to call heapify on, say, like, 256 or something like that, it wouldn't work. That's what you're thinking? I think the main thing is, let me see. Right, because if I wanted to remove an element, right, like, I don't know, 13, which is not the heap, in other words, I have to then take my last element, I have to replace it up here, and then I take this element and I call heapify. Now the thing is, heapify obviously can have a maximum of calling, I believe, 3 times in this tree, right? In this case, though, I'm only going to call it, I believe, 2 times. Once. Oh, well, okay, I actually don't even need to do it there. It's just once. There you go. Well, I had to do it twice to be like, oh, okay, I can't hit this. I can't go here or here. So that's actually 2 times, in fact, but it's not, it's not like a log of, 1, 3, 7, 9... Because a log 9 is going to be 3 times, yet I only had to do it twice. So, I see what you mean. I don't know. I don't think it would be considered a type bound. Like, I honestly don't know why it says theta, but I think it's because... Okay, I know why. It's because it's the worst case. A case you're mentioning, right, is like that case that I just said is like, that's not a worst case, that's just a case, right? It's not the worst. Yeah, it's given that you need to find the worst case time. And since that's, essentially you could say it's only one case, then it should be theta, right? Because it says worst case time. So it has to be theta because you're saying, okay, well, the worst case is always going to be log n, right? That's what theta means. It is just straight equal. So that's why. Right. You wouldn't, yeah. You wouldn't say a worst case is, 1 if you can also do log n, right? So yeah. That's why it's theta. Does the actual log n part make sense? It's because it's based on the height of the trees, not the actual elements themselves. Is that good? Okay, good. Worst case is always theta. Yeah, If you're given the worst case, okay, yeah, if you're given the worst case for 6a, which is, it literally says, then you can say theta because, like, okay, that is the worst case possible. I can just say theta because I'm only looking at one specific case. Yes. Yeah. You are essentially given a specific case that you can find, which in this case, conceptually, how would it have to be worded to be O? I don't know. What is the, like, I don't know. What is the... I mean, it'd be like, you could hit any of these cases. Like, what is the, I don't know, the range, not the range, but, like, what is the, I guess, the big O, I guess. You could ask that. Like, what is the big O of heap remove or something like that? Like that, You could ask that. Upper bound of delete. You could say that. That could work too. Alright. That's good. Anything else on this one? Yeah, no problem. So that should be it for the mock exam. This one was a lot easier. It didn't take 3 hours straight. Thank goodness for that. But at the same time, I didn't really feel like that we went over a lot. So I'm thinking we can do more examples of just general questions. Mainly the time complexities. We do need to go over more of them because there's only one and we're guaranteed to have 4 on there, right? So I wanted to kind of explain like what types of questions you might be getting for question 6. I believe they're mainly going to be focused on heaps, or like maybe not just heaps, but also disjoint sets. I'm trying to think what else the complexities could be focused on. Let me look at the exam real quick, because I'm kind of working in the dark here in terms of like what the test will actually be on. We don't really know as TAs what the tests like will be specifically on for like questions like this, where there will be similar questions. So I'm trying to like kind of guess or estimate what it could be. For sure, min heap questions about time complexity. That's without a doubt. And for sure, disjoint set questions on time complexity. That is also going to be on there. Those are the 2 main ones I can think of when it comes to this unit and complexities. I don't think BFS, DFS are going to do anything like that. I don't think that's going to mention anything in terms of time complexity. For graphs, no. I don't think so. That doesn't really sound like it makes sense. It should be pretty obvious. I guess in case if it does, try to ask it. But it's just going to be your complexity seems like it's just going to be O of n, because you just have to traverse every vertice to make every relationship for every vertice. Like that seems pretty simple enough. For both BFS and DFS, you just have to go in every vertex once. So that should be about it. But that's it for the graphs and stuff. Otherwise, Kruskals and Prims, I don't think those would have any form of like, time complexity. Like all you could say is like, oh, I had to go through every edge for Kruskal and Prims. Otherwise, it's like, okay, like that was it. Like there's nothing else, right? It's not too hard, right? OE log V. Oh, okay, edges times the log of vertices. Is that for Kruskals or Prims? Is that for both of those or what? Both, okay. Actually, I want to see how that works. Why is that? They might ask that, actually, now that I think about it. Why is that? 1, 2... For Kruskals, you just have to count the number of edges and then get E, right? So, okay, so what big O E log V means, it's the number of edges times the log of the number of vertices. That's it. That's all that means. Yeah, my question is why? Like, I think Prims I get it, because for Prims, right, you have to go through A, right? And the worst case is you have to iterate through every edge. So the edges part I get. The log V part is what's confusing me. I'm not sure about that. Why is it that you need log v in addition to that? Do you have to go through? And you have to go through each vertex. But if you were traversing through all the vertices, it wouldn't be log v, it'd be v. It would just be the number of vertices. I know you traverse through all the edges. That's why you'll get, like, edges, but I don't know why it's log v. Log v insinuates that you only need to go through a couple of the vertices to get all of them. I mean, yeah, it is a tree structure, so that, I mean, that could, I don't know, but because when we did prims, let's say, let me go back to that question when we did prims, real quick. When we did prims, right, we started at A, okay, and then once we did A, wait, is this prims even? Oh, it's not. Oops. Let me get out of here. Let me go to the prims question. When we did prims, right, let me erase all that stuff. When we did prims, okay, we started at A, which is 1 vertex. Then we go to D, which is 2, B, which is 3, C, which is 4. And then, I mean, once you do that, then it's just E, which is 5. Which theoretically would be like, oh, I think we went through all the vertices. At least that's what it would look like, except you're not really actually incrementing through the vertices here. You're just like looking at all the edges. I'm not sure why it's log v. You know what? I'll look it up. Hold on. We'll have to look up Google sometimes. Let's see here. Kruskal's time complexity. GPT can't add 1 and 1. Oh yeah, right, I forgot it uses a queue. Oh, no wonder. Okay, never mind. It uses a heap queue, doesn't it? Wait, it uses a queue, doesn't it? I'm pretty sure it does. If I remember right. Let me actually wait, we have pseudocode. What am I doing? Wait, we have pseudocode. I'm being dumb. If you really want to ask like why, you know, complexity, this is where the cheat sheet comes in handy. I should have done this in the first place. The cheat sheet is for sure going to tell us, like, at least give us an idea of why it's that. So, let's see here. For each vertex, you add it. Oh, wait, you just set them. Okay, that's whatever. I guess we can ignore that part in terms of that. R key, and then we have some sort of, I believe this is a heap queue. Okay, so we insert Q, U for each vertex. So I think we're assuming that all of this stuff is already done. Like, this is just inserting every vertex into Q. Okay. Oh, right. None of these functions matter. No, you might go through all of them, but the problem is, even though that's like just big O of V, right? It's outside. It's at the same scope as the actual while loop that like figures out everything. And so if that while loop turns out to have a larger time complexity than both the top 4 loops, then the 4 loops are just insignificant. They don't matter. You don't have to care about them in terms of calculating overall complexity. And considering the fact we have a while loop with a for loop inside it, both of those are probably not going to matter. Let's see. While Q is not null, U is extract min. You extract the minimum for each vertex within the adjacent. If V is in Q, and oh, okay, then yeah, that's what it does. All right. For each vertex in graph V, E comes in, right? So this is for Prim. So if it's in the adjacent, right? Oh yeah, because you have to go through every single V in the adjacent list. That would make sense. Hence the whole, you get that. Mainly, like, you get all the E's coming from the fact that, like, you have to go into the adjacency list, which the adjacency list is E, right? So that makes sense. I know, I'm trying to go through the code bit by bit. And then you just have an if statement, which is fine. You call decrease key. Oh, wait, it's because decrease key is inside it.
That's why. That's why there's a log v, because decreased key is in it, and that's log v, isn't it? Because decreased key has to actually move the node back up. That makes sense. Okay. Because remember, decreased key, the point of it is if your node is on the complete bottom, then you have to move it all the way back up until it's in the right spot, right? That's log v, right? And then this function here, the rest of it is just e. So that's e times log v, right? You execute line 9 for every node. Line 9, u is equal to extract the minimum from the heap. That's just a while loop for the edges, I believe. For each vertex, and then just a while loop in general. You have to do n. Then you do a for loop for every edge. So the for loop is where that e comes in. And this is just while q is equal to nothing. You put everything in q. Right, because you put in, okay. Oh, that's strange. Let me look it up. Hold on. Okay. Priority queue with a time complexity of log e. What? Hold on. Let me ask. let me ping the professor, see if he gets on. I'll ping him and then I'll try and find this in the meanwhile. I want to just make sure with him, but you need to see. Here, I'm gonna take this stupid thing real quick. Let me get that. We're gonna have to discuss this because this is actually a potential test question. I should have known. Okay, look at this pseudocode. What is the actual time complexity of this? Okay. So then, let's see. This is going to be what? Big O of n, of v, right? You just putting every vertex in there, that's it. This is big O of 1. Okay, that doesn't matter. This is going to be what? We're saying big O of v? Is that what we'll say? Okay. So those are the ones up there, and since this is going to be much larger than the ones up there, we can ignore those. Those aren't going to matter. So we have some sort of while loop, which in the large scheme of things, we don't know, okay? So we have extract min. Extract min, if I remember right, you have to delete the node and then get it back, so that's going to be log v. That's fine. We have that happening, and then we have a for loop for each vertex v in the adjacency list of u. Okay, that's fine, that's not too big. So if we're doing that, this I believe is going to be where the edges come in, but we'll see. And then this is just an if statement, that's just going to be big O of 1, I don't care about that. Decrease key is going to be big O of log v, I believe. Let me go on and do that. Let me check and make sure. So decrease key is big O of log v. Yes it is. Yeah, okay. And we got all that stuff going for us. So we gotta go on and get this entire for loop. So this for loop is going to be for each vertex in G adjacent U. I believe that's where the E comes in, right? That should be where the E comes in, and because the adjacency list for every vertex, you're going to check every edge and see if that as a... You're going to check every edge for every vertex and see if, you know, these keys matter and stuff. So I believe it's because of that, that's where the big O of E log V comes in. Right? And then with all of that said and done, that's where the E log V comes in with the algorithm. And then this whole thing, right? This whole, like, while the queue is not, not empty, that's going to be where like the V, because the Q was populated with all V, so then that's where the big O of VE log V comes in, right? And that's what we can conclude with. Oh, Imad, you're here. Can you conclude this? This seems to be right to me. What's the question? Oh, it's just what is the time complexity of that pseudocode? That's it, yeah. Yeah, they should be E log V. I think the main reason is because aren't both of them supposed to use a thingamajig like, wait, what's up? I mean, yeah, I don't think we had this on our test last time though. But just in case. He's mainly going to ask about the discrete sets and the heaps. Those are the main ones I'm thinking of. Oh, question 6. I was going to say that. E is greater than or equal to V, which is just E. The number of edges is greater than or equal to V. The max of E and V log V. Okay, we have E log V, which is fine. And then the V. That's the weird thing. I'm thinking maybe when it talks about the Prim's algorithm, we have all that stuff up top, which is fine. You have the while loop, right? So like this is the part that seems to make sense for the most part. But Let me check Kruskal's real quick. What is Kruskal's? This thing. Ah. Oh yeah. Oh, that's why. Oh. Oh wait, that makes so much more sense. Okay. Okay, that's okay, wait. I think I get it now. So E seems to not be like the number of, it's so confusing, isn't it? Like E is at most V squared. Let me see, like, I don't know, let me make a thing like this. Let me try and do that. Like that's 3. We have A, B, B, C. How is E at most V squared? I'm just really confused on this. Because, like, I'm trying to figure out why it's E log V. You can't have more than V edges from each node. You can't have more than V edges from each node. Yes, I agree with that. That makes sense to me. So like, if I wanted B to be connected to everything, right? B is connected to A and C here, that's 2 edges. Yeah, so like it'd be V minus 1 is the most number of edges you could have from one node. That's fine. Oh wait, because we're only thinking in terms of undirected. You could do this, right? Because remember that algorithm is both for undirected and directed, like that. Okay. And then that's where the extra number of edges comes in. Yeah. So like this would be like, what? You have 2 coming from there, 2 coming from there, 2 coming from there. So edge must be greater than V, because you have to include directed graphs. So if you have E, it's going to overtake that. That makes sense. He probably won't ask about this on the test. Yeah, this is too hard of a question. I doubt he would ask that. He's mainly going to be asking about, directed, or not directed, disjoint sets and heaps. Those are like the main things he's targeting. I doubt he's targeting this one as much. No, definitely not adjacency matrix. He'd never ask that. No way. I'd heavily doubt that ever being on there. Nah, bro. I'm still confused as to why this is a thing. Because, like, this while loop, this while declaration is really throwing me. It looks like everything inside here is actually E log v, which makes sense, but that while loop is kind of throwing me, so. Whatever, I guess. I don't think it matters too much. I guess v is just supposed to be a lot smaller than e, so that's why they just concluded with e. Whatever. Alright, well, we'll get off of that for now. I gotta think up of another thing, and this time I'm gonna actually do whatchamacallit. I have to do one on the heaps and disjoint sets, because that is 99% chance that's gonna be on there. Okay, I guess I'll just go through and just, like, take all the, up here, isn't it? Yeah, I'll just take these and just, like, figure out, like, why it's what. So let's go on and figure out the time complexities of all of these. Let's start with link, because that one is the easiest one. You should be able to take a single look at this pseudocode and just be able to find it out right away. It's, yeah. You should be able to figure out what that is almost instantly, just by looking at it. There's no for loop, there's no while loop, there's no loop in any way, so yeah, it's big O1, yay. That one was pretty easy. So there you go. You know link is big O1, okay? So there we go. Good enough. We have Findset. Let's go on and get that one. Over here. Now this is probably the main one you'll have to focus on. Mainly because union is just you're linking two find sets. So that's just going to be the same answer as find set, I believe. But otherwise, yeah. Of course, unless if we're doing with compression, right? So, alright, this is how we're going to do it. We have that. Okay, that's fine. So find set is clearly recursive, which is fine. And the main thing that can screw this up is if you're compressing or not, right? So we're gonna do no compression on this one, like this, okay? So if we are not compressing on Findset, then all we're going to be doing is just seeing this, right? So if a of x is negative for some reason, like if a of x was like -3, then we return x. That's definitely just a 1. Like this portion is a big O of 1. That makes sense. Okay, that's fine. Because it's recursive, it should be like that. Okay, otherwise, here we go. We're going to have to do this. We just have to do a of x is equal to find set a of x. So it clearly seems like if I had -3, right, and I had a 1, if I was doing like a of 1, then I'm going to get like 1, and I call it a day. Otherwise, I'm going to have to traverse, like if I did a of 2, right, it is not less than 0. So because of that, I have to actually do the find set, and then I can actually return that. And so how is this going to work? I'm just trying to go through the pseudocode to figure out how to use it. So I don't know. If I wanted to do a of 2 is equal to the find set of a of 2, meaning if I put that, a of 2 is 1, so if I put that, that'll be 1, and then that ends up equaling 1, right? That's the idea. So the idea is it's based on the number of pointers I have pointing back to 1. So if I wanted my worst case scenario, for example, it was like that, right? So like I have all of this, and I've told you, okay, hey, give me the worst case scenario of find set, and this was my example, right? I would have to be like 1, I had to start at 6, I'd be like 1, okay, then 2, then 3, then 4, then 5, then 6. It would just clearly end. So I would say it would just be big O of n, wouldn't it? That would make sense. You just have to keep traversing through the entire thing because it keeps going in a straight conga line. And that would be how you have to do find set. It's log n for find set. Am I being dumb? According to the homework, it was log n. For find set?
Worst case for Findset is big O n. Yes, I agree with that. That's what the worst case for it is. Do you know what question specifically asked that on the homework? Oh yeah, that's true. The assignment might have had compression on it. Then you'd have to deal with something else entirely. Then that's completely different. This is assuming no compression. I didn't compress once on this. Oh, that was with the graph formed using union by rank. Okay, sure. What is the worst case complexity of Findset in a disjoint set data structure with n elements? Oh. Worst case time complexity of a disjoint set structure with n elements. I'm not... How is that log n? There has to be some sort of assumption that was given, right? With the graph formed using union by rank. But like, if you just do the raw thing, it should be just the worst case is big O of n. What is the, how is it that union by rank would change it? Is it just like it will not do this? It's not gonna be like a straight line? Okay. Wait, so you mod, union by rank, would that make any difference with the example that I made here? Oh, okay. So this is just an arbitrary tree that was made randomly, so that's big O of n. Okay. So the homework wasn't one. Okay, that's fine. Sounds good then. Then yeah, this works. I'll clarify it here. Arbitrary tree. No union by rank. Or path compression. Okay. Yeah, this would be Findset with just like if you're not compressing and no other modifiers. So now I wanted now to do a Findset, except you're actually going to be compressing after the fact with PC. Which, in this case, when you have to do that, so not only do you have to do the big O n, because you actually have to find the set, so I'm going to copy this thing over here, right? We can still use this tree. Yeah, an arbitrary tree is like, you cannot assume union by rank, it's just random. So you just don't know. So anyways, so I'm doing Findset, right? So just to like go all the way to 6 is big O of n, right? But in addition to this, now you also have to compress it, so that will actually add something to it. And you have to compress as you go along. So I believe that means you have to do like -3, and then if I did this, I have to go through, I have to go to 1, and then I have to be like, oh, okay, I want to compress it. Oh, this was the first one, so I'm not doing that. I have to go to 2, oh, I want to compress it, so then I have to do this. Go to 3, oh, I want to compress it, so I have to do this. Go to 4, I have to compress it. 5, compress it. 6, compress it, right? So in addition to the ON, I believe you also have to like just compress it, right? But I think compression is just changing a single pointer. I don't think that would actually, that's changing the pointer would just be O1, so I don't think this would add any additional runtime overall, if I remember right. Because all you're doing is just like every like thing you hit, right, you just have to also change its pointer, but that's it. There's nothing else. So that should be fine. This is the first time when you run through it only, though. This is the first time you actually fully compress the tree, you do this. I want to explain that because if you are after compression, if you are trying to access it, it will be completely different. It will be this, right? And I wanted to say, I don't know, Findset 6 again. Okay? After compression, I'm not going to be going through everything anymore. Guaranteed. This is where it's going to be just 1, 2, and then 3. I think that's where the amortize will come in, where it will be A of n, comma, n to access this thing. Because I don't have to do it anymore. I just compressed that entire tree. So now that the tree is fully compressed, I can guarantee that, okay, I only need to go, I don't have to go through, n things. I only have to go through just m of them. In this case, I think m is going to be like how many I actually had to go through, if I'm right. I actually don't remember what m is, but I need to look at that again. But yeah, I believe it should be amortized for this one, right? That would make the most sense, I believe. But this is after compression. Yeah, it's basically a constant. It's like literally just like, yeah, this is how many you have to do. When's the test? Thursday. It's Thursday. Getting ahead of the curve here. Does that work? Let me open it, sure. Yeah, I see it. Yeah, it's all good. Oh yeah, this is yours. I forgot about that. What is the worst case time complexity of M operations of union? Find with path compression and make set, including some make set operations at the start. And the answer, what was the answer to this? Was it the amortized? Okay. Oh yeah, Imad made a mock test for this one, so you guys can actually check that out too. It's linked in the description. That one was really useful, I will have to admit. When we got Ding's mock test last semester, it had 2 questions on it. So, it didn't really help too much. Thankfully, Imad's the GOAT, so go check out that. It's really useful. Oh, by the way, Imad, they don't have to do SCC or topological sort, so just ignore those last couple of questions. And then it was M operations of union, and you have to do N make set operations at the start. Oh, okay, I see. Oh, man, I remember this, but like, I remember this was a thing, but I forgot how to do it. Man, okay. Ugh. Okay. So, you have M operations of union. So I'm assuming the M comes from the number of times you have to do union, which that makes sense. That's not an issue. Okay. And then, well, yeah, because you have path compression, so then you have to do
amortization. So I guess if you had m operations of union, that means you're running it m amount of times. That's where that comes from. And then you also like would just every time you do like say Findset and makes, or mainly Findset, every time you have to do that, that would then become amortized, because the first one obviously will not be. You're actually doing the whole thing, but then after that it's going to be compressed and then it will be amortized, and you can do that. So like what I did here, this is a singular union expression. This is one union, so it's after I compressed. So that's like amortize of n comma n. So if you do multiple unions, it's just, and union is represented by the letter m, then it would just be this times m. That would make sense. Which is why it's m times a of m comma n. Because like the idea is, you have to do this one initially, right? But you only have to do it once. After that, it will equal out to like m, how many times you ran it times a of m comma n, right? So that would be why, for that question. That would make sense. Okay. Yeah, make set is just big O1. That one just doesn't matter. No, it doesn't either. They got no top sort or SEC. Everything else goes though. And they have a bit more of a focus on time complexities, it seems, because I don't remember us having that. But yeah, that should be about it. Okay, I think that was the Findset for with no compression and then with it, right? So we have all that done and good. Okay. And then I guess finally is just union, which union is just Findset, comma Findset, and then the union functionality itself is just big O1. So it'll be like big O1, within that is going to be big O(n). So it'll just still be big O of n, or instead it could be big O of, m, Ackermann, m comma n, based on if you have compression or not, okay? So like, I guess like, this is if you're calling multiple union functions, then you'd do that. If we're only talking about one, this is what it is, okay? So one union function will result in either one's without PC, with PC. PC is path compression. Alright, that should be all the disjoint sets functions, which are probably the more awful ones. I guess there is make set, but that is just one. I don't even know if that would ever be asked. Alright, is that good for all of that? Can we move on this? When I say move on, I'm gonna go to the heaps, mainly. The heap equations, or functions, or whatever you have. Okay, cool, I'm gonna move on to the heaps then. So I'm gonna make a big squiggly, and I'm just gonna, you know what, actually I'm gonna make a new page. Mock 2 exam, and I don't know, it's Q6 heap. That's not a 6. Heap. I could go for some Chipotle. I'm hungry. Okay, cool. So we got heap equations. I'm gonna just list them all. Given to me. We got decrease key. Okay, and then we got build heap. And we got insert. We got heapify. So those are 4. Was there any other ones? I think that was it. I don't think there are any more. Oh, wait, remove. I'll do that one. Okay. I think those were the 5, right? Are there any other ones that you guys can remember? I know you guys did the project, so... In math. Oh,
Oh yeah, yeah. Extract is one, but extract is a specific like type of remove. So I probably just won't. Remove is representing that one. Max. I'm just ignoring that one. Any other ones, or are we good? Is that it? Alright, I'll just say we're good. Alright. Okay, we got remove. Okay, remove we already did all the way back in the original question 6 that was given to us. If I remember right, that one ended up being... let me go back. This one was log n. Yeah, that makes sense. Okay. So this was log n. That's good to know. Now we're going to have to do every single one of these one by one. So I'm going to do heapify first, right? So I'm going to give some random heap. I should probably... Okay. I'm going to build it like a min heap, and then I'm going to want it to be a max heap. Okay? So I'm going to try and convert this to be a max heap. So to do that, I have to go down, right? So, and I have to call it on each... Okay, well, I'm going to heapify once, right? And I say, I want to do the top one, or I'm going to heapify this. So, 3 is, let's see here, max heapify. So 3 and 9 are going to switch. So that's one time I did it. And then 3 and 18 got to switch. That's another time I had to do it. And then I have to do it a third time just to see that, hey, there's nothing on the bottom, so I'm done. Okay, 3 times on that. That was 3 levels. That was a single heapify function, and clearly I did not iterate through all n's. I only did through the 3 levels, meaning that is log n. Okay? That is generally log n. I should probably say, I should probably do this. This is assuming all cases, by the way, if I'm doing this. If I say big O. If I say theta, then I'm going to say like this. I'm saying like, okay, this is for the worst case scenario. So I guess I'll just say theta just to be like, okay, these are all worst cases. Okay. There we go. Heapify is log n. Any questions on that? I don't think so. That one should be fine enough. Okay, good. Then we have let's see here, build heap. Okay. So we're gonna have like what? I don't know. I'll do the same thing again. I'm given a min heap. I want to turn it into a max heap, something like that. So for this one, what I have to do is I'm going to be doing heapify again, right? But this time I'm going to be doing it from a of n over 2. If I remember that right, yeah, a of n over 2 to 1. Okay, so then I have to do it from 3, 2 to 1. I'm going to call heapify. So, and that will enable me to build my heap if I remember right. I could go through all that, but I think I don't need to. I think we all get the point. So this here is clearly going to be n over 2 times log n, which is just n log n for theta purposes. So that's just going to be n log n for that one. If I remember right, he mentioned in his slides once that you could theoretically do just n using proofs and all that stuff, but I don't think we need to do that. Just focus on the pseudocode. The pseudocode will let you know like what you should be playing by, and the build max heap here in the pseudocode clearly is n log n. So build heap, yeah, because technically it could be big O of n. On the whole, like it is technically big O of n. But n log n, like for the code here, that was like the pseudocode is clearly showing n log n. I'll ask him that to make sure, because I'm kind of confused on that too. But yeah, that was the main thing. I mean, I don't know, like over here it clearly seems like it's just going to be, you know, n log n on the pseudocode, so I just assume n log n. But if he says otherwise, I'll switch this. So for now, I'll just put a question mark on those 3. But I'm pretty sure that's just n log n. But yeah. So whatever, we'll save that one for when he answers. But we're going to take a look at decrease key. I want to actually look at the pseudocode for this one. Decrease key, where are you? Okay, increase key, same thing. All right, so we have an if statement that's O1. I don't care about that. And what? Else we're going to have a of I as key. We're going to have a while loop. Okay. Then we're going to exchange it with a of I with a of parent, and then I is set to parent. Okay. And then I is going to be set to the parent of I. And the idea is we have to call multiple times, right? So if I wanted to do, I don't know, I'll take this thing again. I'll do the increase key version. So if I wanted to, I don't know, actually no, I'll do the decrease key version. If I wanted 18, I'm going to flip that with a 0, for example, and then I'm going to switch once, switch twice, like that. And because of that, that is, and then I have to do it again, but I'm the root, so that's 3 times. Because of that, that would, for sure, decrease key is going to be theta of log n. And then you do insert. Insert is pretty much decrease or increase key, but you just like do something extra. I don't know. Get that there. Let me rewrite that so it's. If I wanted to insert 21, for example, I do that, and then. Once I've done that, I have to do, I have to call the increase key function, except they would just move up and all that stuff. I know the homework said build heap is big O of n. It's just, the pseudocode says it's n log n. Like, officially, or like, not officially, but like, technically, build heap is big O of n because apparently it's some large proof that the slides mentioned, but the pseudocode says n log n in terms of how we implement it, so I wanted to be sure by asking Professor Ding how that was. Did he answer? No, he hasn't yet. To see like what he would actually expect it to be. But anyways, so we'll get back to that when he answers, okay? But let me see here. We're gonna go on and check the decrease key, I guess. Where is it? It's probably up here. We're not done the decrease key, the insert. Wherever that is. Wait, really? Wait. Is it not on here? Is there no insert function? Oh wow, there isn't. Huh, okay. Well, whatever. Well, just know that... Oh, top right? Am I just dumb? Wait, I'm blind. Oh, I am blind. Okay, that is. Okay, thank you. So we have heap size, you add 1. You set I, you do that, and then you call increase... Oh, okay, then yeah, it is literally just the same. Insert will just be the same as decrease key. So that's pretty much, which makes sense. The point of a heap is to have log n functions for almost everything. So if you have a heap function and you're just going to try and like work with it, you expect every function to be log n except the actual building of the heap. For the building of the heap, you can expect it to be like on average n log n, but really it could just be big O of n. So I'll write this. I'll just do that for now. So the rest of the functions, though, be certain it's log n. You can always assume that, okay? Just not for the build heap. We have to figure that out still. O of n is probably the right answer in terms of like in general. It's just like the code has n log n, so I'm not sure which one to go with on there. Did he answer? Oh, wait, did he? Never mind. So there we go. Is that, that should be all the question. That should be all of the heap functions. That was all the disjoint functions, and then we also did tackle the prims and Kruskals. That should be it, in terms of all the time complexity stuff. I don't think there's anything else. I'll get to that part in a second. I want to focus time complexities first. That should be it. Is there anything I'm missing on those? Is that everything? Scroll back to, oh, I got you. Wait, hold up. Ah. Oh yeah, here we are. So this is going to be, link is just one. Findset, that's the Findset with it and without it. And then this is after the compression. This is quite a bit of stuff, so I'm going to have these notes saved, by the way, and posted in a PDF file after this, so don't worry about it. You'll have access to it after the fact. What's find with PC on repeated calls? Log in. Okay, well find with PC is going to be A of n. Wait, what's up? Find with PC. Well, when you went through it at first, it'll be O of n. After that, it'll be amortized m comma n. It would be Ackermann, yeah. If you do it once after you've done it, it's Ackermann. If you do it multiple times, then it's the number of times Ackermann. So, okay, cool. All right, I think we're good on time complexities. At least the ones that are for sure. I'm pretty sure will be on there. So, okay. That is all of the time complexity stuff. We've already went through the mock exam. I'm thinking of what to do next. I know people want me to go over that again, which is fine. I'm trying to think about what I want to do. Could just go over your mod's guide. Could you provide? Yeah, I know. Using directed versions. I'm thinking of using your mod's guide because that one has those like versions, which is what you want. Also, his are a lot harder. His are like what I'd expect a test. Well, I would not expect a test to be like it. Rather, they will genuinely like challenge your understanding of these topics. So yeah. What time is it? How long? It's been 2 hours. Okay. Okay then. I will go over. Okay, this is what I'm gonna do. I'm not gonna touch Imad's exam, but after this review, if you need more practice, I do recommend you check out his exam. Let me go on and take that thing real quick since he's sending it to us. Yeah, that's going to be all for time complexity. I am going to paste the mods exam in the notes resources tab. If you need more practice, do them. All right, that is going to be very important to you. It will heavily challenge your ability to, go through all this overall. And if you want, after this exam, you can do the topological sort and SEC problems for exam 3, but it is a really good guide, so I recommend you use it. With all that said, I am now going to start doing repeats, so I'm going to be going over questions again that people want to go over. So, yeah, I can do that now. I know somebody asked to do a directed version of questions 3? What was it? Was it literally was it question 3 and 4? Is that it? I don't remember. 1 and 2. Oh, okay. Sure. Alright, I'll do 3 and 4 first. So, let's go back to, I don't know, here. I'm going to go on and do a directed version of the graph above. So what?